Hi, everyone. Of course, there isn't much space to add some value after the great talks this morning, but I will try my best. It's indeed a good opportunity to have this exchange and to exchange our thoughts and insights about causal inference with the community. And the title I promised the audience today, it's not showing up yet. Yep. The uphill battle for true impact of causal inference in a diverse engineering enterprise. And if you haven't yet noticed, by a diverse engineering enterprise, I mean something that looks like a Bosch. And I'm not from the marketing department. I'm actually a research scientist. And I'm, in fact, one member of an awesome research team there who shared a passion about causal inference and wanted to bring this to Bosch research and eventually to use cases in Bosch business units, simply because we envisioned a great impact of using that reasoning capability in Bosch use cases. But the question is, first, why? And a simple answer is manufacturing. If you didn't know, Bosch is a manufacturing-heavy company. It has plants all over the world, in different continents, in different countries. Many of them are in Germany, but some in the UK, in the US, China, Turkey, Australia, just what comes to mind. And these plants, not only do they produce with high annual yield, but also they produce safety-critical components. Take, for instance, the brake system in your vehicle, or the airbag system, or many other automotive components. They also produce healthcare products, for example, the COVID vivalytic test, or you may not know it more for consumer electronics and professional tools. On top of that, Bosch has a thing for innovation, for best-in-class, and most importantly, for quality. So after the end of line of a manufacturing pipeline, it has stringent quality assessment tests in order to release the parts manufactured to the field. If this is an environment where it relates too much to Bosch, how this relates to causality? And the answer here is that this environment is highly structural, highly modular, which is somehow linked to the main principles of causal inference, and independent causal mechanisms that don't interact or influence each other. And an acyclic graph is one common technique of modeling causal relationships. And if we look at how these environments are modeled, this should already trigger the causal reasoning lobe of your brain. And that's actually the main motivation that we started with. But this is one part of the answer. The second part will come in a few slides. Now for the agenda. For this talk, I will split it into three parts. The first is a review of the literature of causal reasoning and how it emerged into the machine learning literature. How we tried to identify some impact for Bosch use cases using causal inference, what impact did we target, and what impact we actually achieved. And finally, not to make this whole talk all about peace and beauty, we talk about some technical content at the end. So research readiness. I guess this audience is already familiar with the remarkable growth of causal inference research that has emerged into the machine learning community. And I'm taking here a closer look at how it emerged into some of the top-tier conferences. I take two examples here, ICML 2020, and 2.5 years later, NeurIPS 2022. This is a point cloud that these conferences nowadays provide in their websites, where each point is a paper, and it's embedded in 2D space using some embedding technique, and they are rearranged based on some similarity measure based on the content of these papers. And highlighted in green are the causality papers submitted to ICML 2020. You can see already two patterns, one of them on the lower right corner, that causality has its own standalone cluster. It's the own problems that it's being addressed using machine learning, or in the machine learning literature. And it's also emerging as a complementary tool to existing machine learning paradigms. For example, causal aspects of reinforcement learning, or active learning, or probabilistic modeling of models, or data imputation, or something between adversarial and physical models. 2.5 years later, this thing doesn't change. It's still it's yet in a much larger number of papers. You see the clusters growing, and the complementary contributions are also much larger, maybe a little bit larger, but the same pattern still exists. A standalone cluster and another cluster that another contribution that's complementary to other machine learning paradigms. Since this this is off topic, but since this conference is 10 months ago, it's quite recent, it would be informative to have some quantification of the contribution of causal inference in these conferences. So this conference got 72 accepted submissions devoted to causal inference. 2 of them were nominated for Best Paper Award. 4 workshops dedicated fully or partially to causal inference and featuring keynote talks from Berl and Spirits. 1 competition and 1 dataset published for causal inference. Here is also, on the top right corner, the biggest cluster that this conference had, the reinforcement learning cluster. And you can see this, or you can, I highlighted that to have a feeling how large of the causal inference cluster compared to the largest cluster of that conference. OK, that's achieved. And of course, from one keynote to the other in these machine learning conferences, you always see repeating appearance of causal inference. And in Europe's 2022, they questioned the validity of machine learning systems, and they just simply realized that prediction doesn't equal intervention, which is what we say in the causality, that correlation doesn't equal causation. And the same thing last week when I was at the AutoML 2023 conference, they just said feature selection in AutoML is just another way of causal discovery, or could benefit from it. OK, for another audience, I would have gone through this mapping in detail, but for this audience, I guess you're more than familiar with this mapping. It's just a map that we used, a mental map that we use internally to pinpoint where would our contribution be. This is nothing but the ladder of causality, associational queries, interventional, counterfactual, but top-down or upside down. And from left to right, the pipeline one follows when trying to build a cause or to answer a causal problem. First, collect the ground truth from the 3 levels that you might have. Observational to address associational data, or experimental if you can, perform experiments. Or finally, the ground truth for counterfactual queries. We think of it as being the expert knowledge, because this is the embedded knowledge and the imaginative process of humans. Then you put all this into a formal framework, causal models, and we highlighted a couple of them that has been so common in literature, the do calculus by Berl and derivatives thereof, for example, the signal calculus by his student, or the potential outcomes framework, and use that to answer different levels of queries. OK, with that achieved, we can go to the next part of the talk, which is the true impact of causal inference that we wanted to achieve. And now comes the real battle, or the problem that we have faced in trying to achieve an impact in an engineering company like Bosch. Previously in the literature, I showed that there are 2 patterns of how causal inference emerged in the machine learning literature. One of them is a standalone, and other is a complementary. For many other industries that's not engineering-based, experiments are costly, are time-consuming, sometimes are non-ethical. But for an engineering company, we do experiments all the time. Our experts, our engineers, have built decades-long experience and know how to design experiments in the lab. And actually, the components, they undergo several experiments in the lab before they are even released. So having interventional data, experimental data, is so much cheaper than, say, social studies, for example. So we have AI or know-how that coexist together in such an environment, which could, of course, make good use of causal AI techniques. But we have neurosymbolic AI, for example, that combines the domain knowledge and machine learning. And if we talk about AI paradigms that try to use experimental data, there is a safe active learning or reinforcement learning. They have their policies to interact with the environment to collect interventional data on top of doing experiments as well. If we say, for example, Causal AI can select relevant features to be explainable and to do some stuff that's reliable and stable, well, patient optimization and AutoML nowadays are doing stuff like this. They are not mostly related, or they are not focused all the time on predictive power, but also they are having some heuristics how to achieve this with some explainability in mind. Of course, they can benefit from Causal AI, but this is complementary. And if we think about causal inference being stable and transferable and transportable to other domains because it learns stable mechanisms, well, there are AI paradigms such as transfer learning that take care of this or look into this issue. And it can benefit from Causal AI, of course. But what are the unique problems that can be only solved using Causal AI that hasn't been addressed using other techniques? And if we look at the previous map, we thought the unique thing that characterizes AI is being able to answer counterfactual queries. Because this is something that is not yet, I mean, at the time we built this, wasn't there yet. And it seemed to have no ground truth except just the imaginative power of humans. Maybe at that time we didn't have foundation models. Maybe the discussion would have been different. But at least for that time, we thought Causal AI is unique on doing counterfactual analysis. So this is where we thought the biggest impact of Causal AI could be, trying to do counterfactual analysis with Causal AI rather than answering associational queries or interventional. And this aligns perfectly with one of the most persistent and annoying problems we have in manufacturing, which is root cause analysis. In manufacturing, especially if you really care about quality like what Bosch does, then you may scrap a part after it has gone through a very lengthy and complicated and costly manufacturing process just because it didn't meet the quality criteria or quality standards that you have bought. And this occurs, by the way, quite often. The manufacturing plants manufacture something like 200,000 pieces a day. Each one costs like, I don't know how much, but okay, some money. And if it's a continuous burn of money, if you keep just scrapping parts like this simply because you don't meet the quality criterion. And it's even more waste of money if you stop your production, guide your maintenance efforts to some stage which is not the root cause, and you then rerun the assembly line once again just to figure out that a couple of days later you get the same issue once again. So identifying the root cause that might lead to a cascade of failures, by the way, until it reaches the quality audit failure is one important problem that we have daily on manufacturing pipelines. And it's addressed nowadays, or the state of art, using manual effort and lengthy RCA protocols. That's done whenever the human investigators, they have, or the engineers, they have enough capacity to work on the problem that's found in the assembly line. So it would be great alignment between the counterfactual capabilities that Causal AI provides and the persisting problem we have in manufacturing pipelines. So that's what we thought. Like, the true impact, or the biggest impact we can achieve, is doing counterfactual RCA using causal analysis. But that wasn't a great success, I have to say. The thing is, indeed, these environments are pretty structured, which is good for causality. And we could use the counterfactual reasoning from causal inference. That's good. But we faced so many challenges. One of them is that these models are quite complex. Like, OK, one step back. So causality, the ladder of causality is simply saying that causality is a cascade of ill-posed problems. You have data, finite number of samples, and many distributions that can fit this data. So you have to make some assumptions. You have to throw some assumptions to identify a unique distribution. And then many distributions, for one distribution, many DAGs, many causal graphs can fit that distribution. So you have to throw even more assumptions to get one DAG. And then many functional causal models that fit that DAG, so you have to throw even more assumptions. And by the time you are able to answer a counterfactual query, you have thrown so many assumptions that you can be questioned along this cascade of L-Boss problems anywhere. And counterfactual RCA is on top of that, on the peak of that pyramid of cascade of L-Boss problems. Add to that, once it reaches the top, it's to answer counterfactual queries using state of art, it's hugely computationally intensive. And for a huge graph that, I will show a graph in a minute, that shows up in a manufacturing pipeline, in a complex manufacturing pipeline with interacting root causes and so on, this doesn't scale. Add to that also that these environments are quite dynamic. They change over time. Each machine that keeps moving an arm 200,000 times a day to some position and gets back and to the same position again, keeps changing its initial conditions every time until at the end of the day, you might get an error just because the state of the machine changes. And of course, in this manufacturing pipeline, you have so many mixture heterogeneous mixture of data types that you should deal with. Starting from the IDs of the suppliers, the timestamps of a process, the numeric data types, of course, the categorical data types. So you have different data types. And all these are challenges that haven't been yet addressed from causality perspective. To give a feeling, we actually released one of the simple manufacturing processes. It's just a press fitting of some valves inside a pressurized chamber. And actually, this is released together with a library to synthesize some data from an imaginary assembly line that looks as complicated as this one. And you can see already how large scale that graph is, which is synthetic and is one of the smallest assembly lines that you can imagine. Now, trying to do root cause analysis on this, it's not an easy task. But along the way, when we tried to achieve that, we realized we have achieved another impact that we didn't envision at the beginning, which is simply putting a causal model. This is an example. This is just anonymous, some samples that don't make any sense for you right now. But actually putting our knowledge on the table together with the engineers so that we can discuss cause and effect relationships in an intuitive language was so much success. Because for a long time, when we as a machine learning experts, when we achieve or we celebrated so much the predictive power of our models, and even when we do like plus 5% above the state of art, we celebrate, but our end users, our engineers who would eventually use these models didn't share that excitement with us. They take these models with some happy faces, but at the end they don't deploy these models into real products because these are safety critical, they don't trust it, they don't know how to use them. But once causality got involved and we could agree on some principles or some intuition or some features to use, things started to change, and they started to take our models with some more confidence. Maybe with a grain of salt, they didn't just blindly take the models, and we still have some arguments, but on the modeling part, not on the machine learning part anymore. But at least they started to build some confidence with these models, started to take them into action, to use them and give us some feedback, what to change, and how to deal with other aspects of machine learning. So the real impact we have achieved was not in the counterfactual part of causal analysis, was actually in the modeling part. And this gave us a language to deal with our end users of machine learning, which aligns, by the way, perfectly with the morning talks. OK, so true impact, we envisioned counterfactual RCA, but we actually achieved structural causal modeling as a big impact for us. Now, for some technical part, say an appetizer for lunch. We did some work on causal discovery. Actually, we also did some work on counterfactual RCA, but I hoped it would be finished by the time, or it would be released by the time I'm here so that I can talk about it. But it will be released soon in 1 or 2 months. So hold tight for that. For the moment, I can only talk about a causal discovery algorithm. It's called VisAI, variation-based cause-effect identification. It's already published. And what it does is that it tries to figure the causal relationship between 2 variables in a system from pure observational data. It's up there in the top right corner. And the question we ask, if we had a distribution of samples from a bivariate system, only 2 variables, how can we tell if X causes Y or Y causes X? Those of you who know Pearl's work would know that CI tests won't apply in this scenario, but we have to use another principle. The principle that's commonly used in these situations is the independence of cause and mechanism. Cause is here, for example, X, and the effect is Y. And if these 2 mechanisms are independent, they don't interfere, they don't share information with each other, nor do they influence each other. And many techniques test for this postulate simply by measuring the mutual information between the 2 mechanisms in information theoretic sense, like colomographic complexities, but they are not computable, so they use proxies of that, like minimum descriptive length, and they check if these 2 mechanisms share any information. We take another approach where we actually test it by the same thing, the same principle we do with intervention, but now we call it variation because we are in, this is a more common term to use in probabilistic sense. So we introduce some variation in one of the mechanisms. Of course, this will be reflected in the final product, in the joint distribution between the 2 random variables. But we ask the question, do we also see it in the conditional? And if we see it, then these 2 mechanisms are not independent. If we don't see it, then it's more a relief that they could be independent. Let's keep this picture with us and jump ahead to the results. This is a result where we introduce more and more variations. So on the x-axis, we introduce more variations on the marginal of x. And on the y-axis, we quantify the influence of this introduced or injected variation on the conditional of y given x. And if you haven't figured it yet, this is the causal direction. This is sweet, nice, horizontal line that shows that no matter how much variation we introduce on the distribution of x, our conditional distributions don't change. While in the acausal direction, they keep just changing. Of course, it's noisy, but if we regress it, we just see a trend going always up in the acausal direction, while the trend is almost constant in the causal direction. This is a great indicator that we could use this technique for performing, for identifying the cause and effect in a bivariate system. Now, how do we treat it mathematically? I mentioned that we will introduce a variation so that we change one distribution from B of X to B of X with this lightning bolt. But this cannot be treated mathematically, so we introduce this quantifiable parameter alpha. And alpha is nothing but a reweighting of the samples. So to be honest, this B of X is nothing but a distribution you estimated from the samples that you got. And if you put some weights on the samples, so you change the weights of these samples, the importance of these samples, you get another distribution. This is nothing but the same technique that have been reused over and over again to balance some class imbalance data. OK, so we put some weights on the samples, and we want some measure to quantify the divergence or the distance between these 2 distributions, B of X and B alpha of X. You have a bunch of discrepancy measures, KL divergence, Jensen-Shannon, total variation, a bunch of them, but we wanted something that is mathematically easier to treat. For example, to handle any data type, to be computable from a finite data set efficiently, and so on and so forth, to be symmetric. And one good choice for us was MMD, maximum mean discrepancy, which is symmetric, which is applied on a kernel. So you can just define a kernel on whatever data type that you have and quantify the discrepancy between the 2 distributions. Great. So how do we introduce a variation? We take this MMD and maximize it with respect to the variable parameter alpha. Of course, we need to make sure that this is a valid normalized weight vector, so we add a couple of constraints. And looking at the, sorry, one step back. So this is our optimization problem that gives us 1 point at the extreme of the graph. It just maximizes the MMD between the two distributions, gives us one maximum value at the end of the graph that I showed a couple of slides earlier. To regularize this, we just add one more scalar value, scalar parameter P alpha, that ranges between 0 and 1 and penalizes how much we can introduce of a variation. Looking at the estimator for MMD, you can see it has a quadratic form with respect to both the data types, the data, so it's a kernel, this K matrix diagram, the gram matrix, and of course it's also quadratic in terms of the alpha parameter that we want to maximize with respect to. So this already is close enough to a convex optimization problem, only that it's being maximized rather than minimized. We have a mathematical treatment for that. But at least for the moment, this is quadratic. These are all linear constraints, so you can use, so for example, CVX pi to solve this. And once you do that, you get a distribution of B alpha that looks like this. It puts all the weights in the outliers, so that it picks only the samples that are from belong to the tail of the distribution and puts 0 weights on the bulk of the distribution, so that these two distributions are entirely different. With that, we have already introduced a variation. We need to quantify this on the conditionals. This is not as easy as the other one, but at least still we have a way to deal with it. I will skip it in favor of time. So these are the results that we have. They are competitive to existing state-of-art, not that superior to state-of-art, but at least we throw this result, this nice outcome as this one, as future work to explore this kind of technique for identifying cause and effect relationships, which actually concludes this technical part by introducing another mechanism to identify cause and effect relationships in a bivariate system. Now, this concludes my talk, but instead of having a summary, I would like to have one more slide, not to mention that I forgot LLMs. No, so they are there just to give you one of the perspectives that I have from causality side, which is similar to what happened 10 years ago. Like those of you who have been in the field of machine learning 10 years ago, I'm not that old, but I lived those days because it was the first year of my PhD. When this paper, AlexNet, came out, it showed an increase in performance of almost 10% beyond the latest algorithm that achieved the same, that was performed on ImageNet at that time. And it was received first with some skepticism, later on with some careful use, and eventually with wide adoption across various domains, deep learning. And nowadays, 10 years later, we have this paper that says causal reasoning and large language models opening a new frontier for causality. What they do is that they show that the Tupingen dataset, which is a challenging dataset for cause and effect identification, was challenging for many techniques of causal inference, with the best achieved 83%. Now, just asking ChatGPT to solve that problem achieves more than almost the same, so almost 12% increase in performance and detection accuracy. And it's still at the phase of skepticism, because even in that paper, they question whether or not this is a genuine result, or is it just ChatGPT memorizing the results of Tupingen dataset because it's open world, it's published. And I think we will soon enough move to the second and third phase. But for the moment, this is just a replay of the past. With that, many thanks for listening, and I conclude my talk.
Thank you. Thank you very much for that. Yeah, fascinating to hear how causality is applied to yet another industry over the course of this morning. So are there any questions from the audience, both in person and online? We have one over from the right-hand side from Tom.
You mentioned that the causal modeling part was one of the big wins that you got. Was Was that because of the effect estimates or purely from that communication piece that it gave you a shared language with the domain experts? And off the back of that, where do you see this going in the future in terms of building further in this use case and building on top that causal model?
So maybe the first option, so the communication or what, sorry?
So like you mentioned that it helped you and the kind of domain experts speak the same language. Were there other more quantifiable benefits of it in terms of treatment effects or kind of predictive outputs and that sort of thing? And then where do you expect to take it in the future?
So yes, it was mostly communication with the engineers because we were not focused on treatment effects or quantifying the causal influence, even though these came along on trying to solve the problem of root cause analysis. But we had our eyes more focused on solving the problem of counterfactual RCA more than anything else. And eventually we found ourselves having these more confident discussions with the users of our models way more than that we did before. For years, we have been like, BCAI was there for 6 and 7 years now. And these models built or showed more hope in transferring the machine learning models to the eventual users way more than before. So the communication is the biggest win. Of course, there could be some other wins on the way, but we had our eyes more focused on the counterfactual RCA.
Great. One more question here in the center.
Thank you. I really enjoyed your talk. What was the P alpha function doing? I kind of lost it there. What was the purpose of that? What is the innovation in the paper that you had? Because I think varying both distributions and then checking the conditional is a standard idea.
Varying what, sorry?
Varying the marginal and then checking the conditional is a standard idea.
So the standard idea from literature is that one would, okay, let me jump to it. One would try to identify the mutual information between the two. So here K is a columograph complexity that shows how much of a complexity this distribution looks like. And if it shares some knowledge with the other distribution, the conditional, then this knowledge would be redundant, and one side of this inequality would be larger than the other. And of course, K is not a computable quantity, so the proxies thereof is, for example, S here, quanti-regression scores. They are doing regression and stuff. But again, they are proxies of columograph complexities or minimum descriptive length. Trying to change one distribution and quantifying the effect on the other, I'm not talking about changing the variable itself. I'm talking about the mechanisms, so one level above, to change the mechanism itself and see if the other mechanism is changing, not to intervene on the random variable itself to see if I see an effect on the outcome. And this, I think we haven't found it in literature. If there is something like this, I would be happy to discuss offline.
That answers my question.
Sure.
Great. Are there any other questions? Well, with that then, let's thank our speaker one more time. Thank you very much.